Alrighty, welcome back. This is chapter 5. It's actually, I think, lecture 12 is what this is going to be, but we're going to start talking about light and what that tells us about like where the electrons are in an atom. It gets a little crazy, so buckle up, hang on. Lots of books, they'll always show you like fireworks for this chapter because, well, they're cool looking. They're all pretty. You got all these different colors, but that's a lot of chemistry you're seeing right there. So what's the deal with fireworks? Questions to ponder here. So why do we get colors? If I have red light and I have green light, what's different? Is there something the same? Is there something different? We'll talk about that kind of stuff. Why do different chemicals give us different colors? We'll hit that in this chapter. This is a really good one. Like, why don't electrons crash into the nucleus? All right, so you learned in the previous chapter that we have electrons, these little negative things, and you learned about protons. Those are in the nucleus. And you've learned now that opposite charges attract, so negatives and positives, they attract each other. Why do the electrons just go blip and stick right to the nucleus? Like, why do they stay out of there? So we're going to cover that in this chapter, which is really cool. And what does all this have to do with atoms? All right, all these things will be answered. But first, I'm going to tell you a little bit of stuff about light itself. Light, also known as electromagnetic radiation. All right, so like I said, it's the light that's given off by elements that told us a whole bunch of stuff. But to talk about that, we need to figure out some characteristics of light. So light will have a wavelength, there's going to be a frequency, and there's also going to be a speed. All right, so all electromagnetic radiation, all light, travels at the same speed. So going through a vacuum, that's about 3 times 10 to the 8 meters per second. That's 300 million meters per second. It's really fast stuff. All right, so all light's going at the same speed. Now, the other things I mentioned were frequency and wavelength. All right, so if you look at this slide right here, I'll kind of actually hit both of these things so they pop up. All right, here's your little waves. All right, so this is one wave. Here's another wave. Here's a third wave. Here's the fourth wave. All right, the distance between these peaks, that's our wavelength. I could measure the full length of the wave, so I'm starting in the middle and going right here to the middle. So that's the wavelength, but it's easier just to actually go peak to peak because it's the same distance. All right, so that is your wavelength. The symbol for wavelength is lambda. It looks kind of like a lowercase y, actually the reflection of it, and I'll show you that on the next slide. It's this funky letter. And speaking of funky letters, the frequency, right? This thing looks like a letter V. Might look like an italic V, but it's actually the Greek letter nu. All right, that's spelled N-U. It's nu. So frequency is nu. Frequency is how many waves pass by per second. So imagine this is a 1 second pulse of light. This is also a 1 second pulse of light. All right, this one is going to be a higher frequency light because there's more waves per second than over here. All right, so you can see there's a relationship between the wavelength and the frequency. All right, so the longer the wavelength is, the lower the frequency. So they're inversely related. All right, so don't forget, that's a nu. That's not a V, it's a nu. And here's lambda. Here's the thing I said looks like the reflection of a Y, but that is your wavelength. So I think lambda, wavelength, length, lambda, lambda, wave. When you hear electromagnetic radiation, the reason it's called that is because there's an electric field that's going up and down, up and down, up and down, and there's a magnetic field that's perpendicular to it, going back and forth, back and forth, back and forth. All right, so that's why we call it electromagnetic radiation. And there's like a lowrider cruising by outside, blaring its stereo. All right. Back in, I think it was around 1666, Isaac Newton took regular old sunlight, white light, and split it into its components. So he used a prism and split it up and saw this whole rainbow. All right, so Roy G. Biv. So red, orange, yellow, green, blue, indigo, violet, that thing. All right, so we have this whole rainbow here. These are the wavelengths. So you don't need to memorize these numbers, but it's just kind of good to have a ballpark idea that are the colors we see. From red all the way to violet, it ranges from about around 750 nanometers to around 400 nanometers, right? But there's a lot more. In fact, we only see a little sliver, right? There's a whole lot more out there. So radio and television waves, really, really long wavelengths. They can have wavelengths that are hundreds of meters long. I think even some that are like thousands of meters long, which is crazy. Really, really long wavelengths. And then you get up to microwaves, and then the wavelength is even shorter. You get to infrared. And then we hit the little section that we can see. So it goes from infrared, and then we have Roy G. Biv. So red, orange, yellow, green, blue, indigo, violet. And then once you go past violet, you're into ultraviolet, then X-rays, then gamma rays, cosmic rays, and all that stuff out here. So really short wavelengths out here. Really long over here, really short here. So we only see from about 750 nanometers to about 380 nanometers. That's the only stuff that our eyes can pick up. At least most people. I think I've heard some stuff. I swear I just saw some other stuff. Like some people have just a little bit, maybe on either side here. They can see a little extra stuff. So that's kind of cool. It's like a superpower. All right. So to answer that first question I was talking about, like what these different colors of light. So here's like a purple light and here's a red light. So how are they the same? Well, light is always going to travel the same speed, no matter what color it is or what wavelength it is. But it's the wavelength that gives light its color. All right, so 700 nanometer wavelength, that is what we see as red. 400 nanometers wavelength, that's what we see as purple. Cool. All right, I'm going to stop there. I'm going to start getting weird in the next part. So the next part, we're going to start talking about quantum mechanics and the quantum nature of energy and crazy stuff like that. All right, see you then.